Welcome back. Now we are going to look at some of the structural properties first, which is called radial distribution function. As I had mentioned earlier, it's an important structural parameter because it tells you how the atoms are distributed and what kind of structure they are creating with respect to each other. And that's where it is important to look at how many nearest neighbors, then second order neighbors, third order neighbors are as we go out from a central location of the particle. So, that is why it is called radial distribution. So, if I take a central atom and then I go radially out and I am looking at certain shells and see how many particles I find in that particular radial distance, then I can find what is the radial distribution of particles from that central atom. Now, let us say if you had a very regular particle distribution like in a crystal lattice, then you expect certain number of neighbors to be found because they are located in a regular lattice structure which is repeating itself. So, if I take an atom and if I go radially out, then I can immediately for that structure I will have certain number of neighbors. And if I know those first neighbor, second neighbor, third neighbor as I go radially out, then I can identify what crystal structure I am looking at. So, that is how the peaks of radial distribution function, which essentially show number of neighbors at a certain distance from the central atom, and we are now looking again averaging all atoms. So, now if we do that, then we will know exactly what kind of structure we are looking at. And if there was no structure, and as we look at particles moving all around and they are not following a particular static structure, then you will know that this is a moving system, dynamic system. It is not a crystalline structure, it may be amorphous or it may be liquid or it may be even gaseous phase. So, this is a structural parameter which shows order and how system goes from order to disorder. So, as we look at the ordered system or crystalline structure, disordered systems are either liquid or gas. So, we are going to look at that. So, looking at your slide now, radial distribution function is defined as G of R, where we are looking at the density of atoms, local density over the density of atom, the volume. So, as you look at this is a very simple definition. It provides us information about the density of atom at a given radius r. So, we are essentially looking at number of atoms, especially in the number density sense, in terms of as you move out of the central atom. So, if you look at G of R, you can also define in terms of average number of atoms that I am finding in a shell, which is r plus minus delta r by 2. And then we are also looking at the volume of this shell, and so I am looking at the number density at certain distance r. So, if I go to G r 2 pi r square dr, this is the number of particles lying in a spherical shell of radius r and thickness dr. So, think about this as a radial space and think about these two spheres at distance delta r. You can look at this, and now you are trying to find how many atoms are in that particular shell, which is delta r from a radial distribution of the structure. So, now if you look at this, we essentially are able to find the radial distribution G of r for a pair potential by looking at a distance r, and you are looking at delta of r minus r I j. So, let us say if we take an arbitrary distance from r I j, which are the two pair potential, and then look at that point sum all the particle and see which particles we find in that shell, and then we divide that by the volume of the system over the number of atoms square. Now, we are looking at G of r for a what we call as pair potential function like Leonard Jones, and that is a very important parameter as we said. So, here is interpretation of that shell. So, if you look at your slide now, these are all the atoms around. I am going away from the central potential. This is the nabla r plus minus delta r over 2. This is the shell, and in that I am finding these blue balls, which are the number of atoms that we have. So, consider the volume, and if you look at their G of r n r plus minus delta r by 2. So, this is g of r, and particle density then becomes sigma, which is equal to n number of atoms over volume of this shell. Now, the good part about this function is that it can be also calculated using neutron scattering experiment. What neutron scattering technique does is that it will throw a beam of neutron on a particular material, and then they will bounce off as they hit particular number of atoms there. So, if you look at the spatial distribution of neutrons that are coming out of this collision, then you can see how many collisions happen in a particular shell. So, you can calculate g of r from neutron scattering. That is an experimental technique which is well established. So, by calculating molecular dynamics simulation of g of r, now you can also calculate a experimental parameter. Always our effort is to calculate something using molecular dynamics simulation with a bulk property or a experimental property that we can compare against, and that is how we can validate how good is our simulation. So, in this case you are looking at neutron scattering as a means to look at that. Now, you can also look at g of r, as I was explaining to you, in terms of the phase transition between solid and liquid phase. So, let us look at on your slide how does the g of r looks like in a solid phase. So, if you look at in this case you are seeing 4 peaks. Let us say this is phase centered cubic g of r. So, you are looking at the first neighbor, there is certain number of atoms here, then second neighbor. So, let us say there are 8 atoms here, there are 4 atoms here. So, if you look at this is about 6 atom under this peak, so if you integrate, let us say there are total 8 atoms here. Then if you look at the second peak, there may be 4, third one may be 6, another 4. So, if you calculate these nearest neighbor from the crystalline structure perspective, you can see that these peaks represent that FCC structure. So, if you calculate based on the time average trajectories of g of r over all pairs of atoms, and you find this kind of a plot between g of r and looking at the intensity of g of r, which is a radial correlation, radial distribution function, and the distance from the central atom. Now, you know that this is a crystalline structure because these are stable peaks. Now, as you go to a liquid phase, then you see that there is a softening of all the peaks, and there is only one peak, and that has become much larger. So, what you are seeing is a large number of neighbors are around that from the first peak, around the nearest shell, but then after that there is no correlation, there is no peak coming out, and there is the softening of all the other peaks. A peak indicates a particular favored separation distance for neighbors to a given particle. So, thus RDF reveals details about the atomic structure of a system being simulated. So, now in this case is solid phase with the certain number of atoms in crystalline structure. This is the liquid phase where you cannot find, and there is essentially diffusion of the atoms around that particle, they are moving around. So, you do find certain number of atoms around a central particle, but you can see that that has no peaks after the first one, which is essentially assembly of all the particles. So, now if you look at the first peak correspond to the nearest neighbor shell, the second peak to the second nearest neighbor shell, etc. So, if you look at in this case, now we are looking at 3 different phases: solid, liquid and gas, represented by S, L and G. So, if you look at solid argon here, you can see all those 4 peaks that we discussed earlier. Liquid argon, you also saw that softening of the peak, and then if you look at the gaseous phase of the argon, then you see that there is absolutely no other than the particles which are close by, you can see very there is no peak existing at all after the first shell. So, if you look at in FCC, if you look at 12, 6, 24 and 12 in the first 4 shells, so that represented here for FCC 12 particles in the first shell, second one is 6 particles, third one is 24 particles. As you know, there is a broadening of peak here, and the fourth one is 12 particle again. But if you look at as you go to liquid phase, all of that is destroyed, and in the gaseous phase there is absolutely no memory of the nearest neighbors. So, I think this is shows you very important factor which you can also calculate using neutron scattering. So, now if you look at argon and do the neutron scattering on it, you will get in the liquid phase, you will get the same peaks that we are looking at here. And if your molecular dynamics simulation is correct, you should get exactly the same number of neighbors, especially in the crystalline phase. But then you can compare the other G of R, what we call as radial distribution function. So this is a very important order disorder parameter, starting from an ordered phase of crystalline phase to disordered phase of liquid phase, but some local order that you are seeing in this peak. There is some local order around the particle, but then in the gaseous phase is completely disordered, and there is absolutely no memory or no local structure that remains. And so this is a very important way to identify the different phases. And if you know these three parameters in the solid, liquid and gas phase, and if you calculate the phase transition between these three phases, you should be able to then go back to our understanding of thermodynamics about the phase transition. And in that you can then see what are the potential thermodynamic potential responsible for this phase transition, like Gibbs free energy. And so if you look at the between liquid phase and the solid phase, is the Gibbs free energy is calculated properly so that they can coexist. So you can also understand why two different phases can coexist in a particular situation, because of some of the Gibbs free energy barrier, which allows liquid and solid to remain in their although they are in contact with each other, they still have the two phase system available. So let me stop here. We are now going to look at another property which is called mean square displacement, so you can understand the diffusion of material. So going from structural property, now we are going to go to dynamic property. Thank you.